All right, thanks everyone for joining in today. So I'm going to talk about Clang compiler. Um, so those of you who don't know about Clang, you will get some introduction. Those of you who know about it probably will get to know what has been up lately. Please feel free to ask questions and we'll continue with that. Um, So this is a rough agenda, but doesn't have to be. We can, stop and answer questions or discussions, if any. So what is Clang? So, it is pronounced as Clang, not Clang. It's a compiler frontend, which is basically using LLVM infrastructure as backend to produce code. It's a static compiler. LLVM has many tools that are built using LLVM. Rust compiler uses LLVM. There are many new languages which basically take LLVM and then they add their front ends to it, and then they have a working compiler. So Clang is actually a C++ front end, and it has been since enhanced to do more languages: Objective-C, C++, OpenCL, CUDA, and FLang, which is actually added very recently. So you have Fortran there as well. In addition to just the compiler tool, it has some additional tools that are available for static analysis or any code analysis. And it uses Apache 2.0 license, actually, with some LLVM exceptions, which lets you more freedom to use it in your own proprietary code. So I'll go over a little bit of its design when it comes to the philosophy behind it. So it's written in C++. So it's a huge compiler base. If you compile it, it takes quite a bit to compile the compiler itself. But that may not be that's a worry for compiler writers more than anyone else. The users probably will be happy to use it because in many cases it compiles faster than other compilers. It has been getting slower as new things have been added to it in the past, but it is still very fast, and especially it is fast for C++ templatized code and large files. It has support for architectures, which is way less than what GCC has, but it does support many of the major architectures in the market today. So you'll see ARM 64-bit and 32-bit, IA32 and 64 are primary platforms, are very well supported. These five, both 32-bit as well as 64-bit, are well supported now since Clang 10 onwards. There are ports for MIPS and MIPS64 as well as PowerPC 64. PowerPC 64 is tested, little endian. MIPS 64 probably is least tested, but it does work quite well. It's migrating to GitHub for its development. So you'll find the code on LLVM project handle on GitHub, LLVM handle, sorry. And it does have, it's migrating its, Bugzilla and everything over to the GitHub issues as well. And it's basically a mono repo, which means it combines many other repos into a single repo. You check out LLVM project and everything that you need in terms of sources is in there from LLVM. That includes extra tools and other projects. There's a homepage for Clang. There's a LLVM homepage, of course, but there's a homepage for Clang as well. And you could go there for like documentation and other things. So what are the goals? if you programmed in C++ long ago, you would remember that diagnostics were horrible. You never got to the point what the error was, and you were like sifting through the error messages to figure out what went wrong. So one of the goals was to give you more pinpointed diagnostics and help you understand the issues. IDE integration. So a lot of compilers, they had IDEs, but they at least in Linux world didn't have a good IDE integration. So that was one of the ideas behind it as well. And more compatible license, so you could use it in commercial products, and developer friendly, and fast and low memory use, which I stated earlier, has been diminishing a little bit, but it still is very competitive. And GCC compatible, which means it should be able to compile a lot of GCC compiled code as well. So for that fact, it has implemented a lot of GNU extensions as well. Not all of them though. And modular. So it's a library design, which means you could take the compiler and write your own tool on top, and use libclang basically to get all the compiler facilities underneath. So it's very powerful. When you want to write a smaller tool that will operate on, or you need information about your code flow and other things. So many folks write tools for their particular use cases. I know that people, for example, there were formatters for IPv4, IPv6 addresses and things like that. And those are pretty easy now, given the modular design and the library design that we have. So, and talking of better diagnostics, I've picked up this, 3 examples here. You could try it in your free time, but what you'll see is that it shows the difference. These are not the only one, but what you will see is many of these have improved even in other compilers as well nowadays. So Clang has probably helped the ecosystem do a little bit better. So I'm picking 3 examples here. So if you look into the formatting patch, so there's a warning you will get, and we will see. So you get this warning from GCC as well nowadays, but only when you enable WAL. If you don't enable WAL, it's pretty happy. But Clang will give you a warning, and there is this caret sign, which basically pinpoints it where the issue is really. So that's actually pretty neat. It not only tells you where the problem is, but also gives you the column and points you with a caret sign. The other cool thing that you will see is, so if you look here, it's telling you what's wrong with your code. So it's trying to get you down to basically how you can fix it. But if you were to feed this into GCC, it'll give you an error, but it'll say, oh, there's an error before this, after this, and what the error is, it really doesn't know. So you can see that, it's more clear about its errors. And it also gives you some fix-it hints. GCC doesn't give it though. And I tried WAL, you don't see anything here. But if you try with Clang, it will try to suggest you how to fix it. So if you can see, there's a warning it finds that you have a old style syntax for initializing the structure. And it will basically show you where the error is and try to give you some hint, hey, how you can fix it. So I thought that's pretty cool. So if you are a C, C++ developer, I'm hoping that you'll find this tool pretty handy and hopefully helpful. Now, I'm going to talk about the clang support in Yocto Project a little bit. So if you are trying to use clang with Yocto Project, then we host it currently on a separate layer. It's called MetaClang. You can find it on the layer index, and it's supporting right now all the currently supported releases. You could also find the older releases are there, but they may not be very well supported. So if you're using one of the EOL releases, I encourage you to upgrade to Dunfell and newer, and then MetaClang will also be useful for you there. So we use currently GitHub workflow, which means if you are sending patches, you could send it as pull request to GitHub. There is a CI integration there. It gets tested and things like that. But you could also send it to open embedded mailing lists with MetaClang in the subject prefix, and we can pick it up from there. So how do you use it? Well, basically, if you are familiar with the Yocto project, then adding a layer, it's very similar to any other layer that you'll add. So we use bitbake layers tool here, and you can basically add MetaClang to your core layers. Here you see an example of using Pocky, but you could do similar with the Open Embedded Core or bitbake. So it doesn't have any other dependencies other than the core layer. So you basically can just build with bare minimum. So once you add it, what happens? So your default compiler still remains GCC. The intention is to keep it inert as much as possible, which means that it might add into your dependencies if you use some recipes where it is enforced, but it tries not to change your defaults as much as it can. So now if you want to choose Clang as your compiler, you could do it in two ways. You could choose it per recipe, which means you could say, this particular recipe I want to compile using Clang, and then rest of your system builds using GCC. Or you could basically set it in local.conf for any configuration metadata for that matter, which will basically get you, which switches your system compiler to use Clang at that point, which means every package will be compiled with Clang, except the ones that are pinned to GCC. Some packages currently aren't compilable with Clang for many reasons, and they are pinned actually in a file, in a config file in MetaClang, which is called non-clangable.conf. So you could take a look at that. It's not a huge set anymore, but still there are packages which are not compilable. There's this variable it uses currently, toolchain, which basically denotes what toolchain you want for either your whole build or for your particular recipe. That will choose the compiler. Using basically LLVM runtime is available as well. So if compiler is one thing, but there is runtime associated with the compilers, C runtime as well as C++ runtime. So Clang does provide a runtime as well, and also a C++ standard library. So default remains the GCC runtime, but you could also choose LLVM runtime if you want. So there's a single variable called runtime. You could set it to LLVM, and it will start using compiler RT and unwind lib and libc++, which are basically three components that it will start using and replace libgcc and libstrip++ with that. It still will use the CRT files from the compiler. Clang does provide them, but they have not been yet integrated into the builds yet. So there still will be some components that are some objects coming in from GCC runtime. So you could also switch just your C++ standard library. In some cases, you just want to use libc++ for some reasons, and you don't want to touch your C runtime. You could just set libc++ equals to standard lib option, and it'll just switch your C++ library to use libc++. And you could do it exactly same way for just for a package, or you could do it system-wide. You could also generate like the SDKs. So there's a variable called clang SDK, which basically adds Clang to your SDK. This is required because, say, if you were to add MetaClang, but you don't get to, it'll insert itself into your SDKs even if you didn't want it to. So this variable is unset basically by default, which means that Clang remains inert, and you make a conscious choice to add it to your SDKs. That is when the compiler will start adding itself into your SDK targets. So this variable you would be setting in your local.conf for your distro, or wherever your config metadata is, and that'll help you generate the SDKs, and that'll have Clang. And mind you that it'll have both the compilers in there, so it'll have Clang as well as GCC in your SDK, and you could use either of them when you start using them. There's a variable called Clang CC and Clang C++. Clang CPP and Clang CXX and Clang CC. So these variables are basically defined to just define the Clang compiler. You could set your CC equals to these variables in your make files or your environment when you want to use Clang via SDK. It doesn't insert itself as a default compiler. Your default compiler still remains GCC. So why do we need Clang? So for some of the things that I mentioned earlier, some packages have started using Clang exclusively, and more and more packages, more newer packages are starting to use it. And some of them are supporting multiple compilers, some of them aren't. So that is one reason that we need it and for compiling some packages. And I'll mention here Chromium. Chromium comes from a different layer, from meta browser layer, but it's used by quite a few users in the open embedded Yocto world, and it solely relies on Clang. We have supported that with GCC for some time, but it's not maintained upstream. So there's a lot of work that needs to be done for it to be going with GCC. So when you use or want to use Chromium, you will have to use Clang. And there is BCC and bpftrace, which are also using Clang in different capacities, Android tools, and the LLVM-Translator that SPIRV has. So these are just few of the key components that I mentioned here. And some of them prefer Clang, even though they do support GCC as well. But Firefox, for example, would their primary CIs have been using Clang as well. So there is an ecosystem of apps that are now coming out and using Clang exclusively, and that is one reason why we would need it. But that's not the only one. There are additional tools, and I did talk about static analyzers. And MetaClang has integration for static analyzer, and you could run it by inheriting the scan build class, and you could set scan build for a particular package that you want to scan. So it doesn't have to be the whole system. You could just pinpoint it to one recipe, and that is the only one that will be run through the static analyzer. And what this class does is it introduces a couple of tasks to run the scan build and to run the viewer. So once you scan it, so I just shown an example here. And when you run the scan view, it basically launches a browser, or rather a server on your system that you can open in a browser, and it will show you the output. So, you know, for example, this is how it looks like, and as you can see, it tries to tell you what all different things it found. And you could click on these reports, and it gives you a nice view of what it thinks is wrong there or could be fixed. And you know, you can browse through your files and things like that. So it's pretty neat. What it does is it basically generates, if you do more than one package, it will have all these packages listed here. So you could, you know, sift through them, look through each package and all these issues here. So it's a pretty neat use case that, you know, you could leverage. I personally have reported and fixed many issues in many packages just by running this tool and finding what's up and running. So some of low-hanging fruit sometimes are there, which you can fix in various packages. So, you know, it's handy in that regard. So there are additional tools in there as well. So you can see there's LLDB, which is your debugger, similar to GDB. It also provides you a target agent called LLDB server, which is which you can basically ship in your targets as it is available, and it is also governed under Apache 2.0 license. And it has very powerful CLI. It's Pythonic in nature, and you could do a lot more scripting on command line than you would be able to do with, say, GDB today. So you could write complex, you could code complex scenarios in the CLI when you are debugging and catching use cases. So it's pretty neat. LLDB doesn't work on all kind of architectures. So, you know, but primarily ARM, ARM64, x86, x86-64, they work very well. LLD is the linker, which basically is new, is a very fast linker. So if you use it on some of the large projects like Chromium, you see a significant linking speed increases. When you're writing small programs, you may not see it, but for large binaries, I think it's very, very clear that it's fast.
Does it use more memory when linking, Khem?
No, it shouldn't be using more memory. To be true, I haven't measured it, but it is multi-threaded. So, you know, you might see that, you know, it needs memory depending upon how much cores you have and things like that. But, you know, because the link is spread over its linking time, you know, it's not building up, you know, your memory, because it's not a one process needing all the memory. So it's an interesting question to find out, you know, what's the what's the memory usage profile when it is linking.
Okay, thanks.
Yeah, so other tools that are handy is Clang format, which basically, you know, so I think Clang format actually is provides some formatting to the C++ code, and you could also have other tools like ClangD, which is your language server. You know, when you do cross-referencing in IDEs like Visual Studio Code and all, you know, all those cross-referencing and everything, so that you can basically use ClangD to provide you all that help in IDEs. ClangTidy is actually a linter tool, and you know, this is very handy actually in C++ projects, and you can like easily detect bug-prone patterns. And there are other tools actually, which one of them is called Clang include fixer, which basically checks if you have all the includes are okay, you know, because one of the problems you have in C++ and C code is that you have include this, include that, and you end up including a lot of headers that are not even required anymore. So a lot of time is spent in pre-processing those. If you look at Chromium build, you'll find interesting data. I think somebody did a presentation on that how much of time they spend in processing or pre-processing rather the code. So so the Clang include fixer is actually is a tool for that kind of scenarios. And sometimes you rename things in mass. So Clang rename is another tool where you can rename patterns in the code. So, you know, if you rename variables, functions, things like that, it's very handy when kind of like migrating from one C++ standard to another C++ standard, and some new, you know, keyword got introduced or deleted or something. So it's very handy when you're doing those sort of migrations. Yeah, so there's also a Clang doc tool, which basically helps you create documentation out of your source code. And you know, it can output in several different formats. So in Yocto, we do have some world builds happening today, and regularly tested. And they are QEMU ARM64, x86, x86-64, and RISC-V. So RISC-V, 32, and 64 as well. And in your distro, we use Clang as our default compiler. There are certain packages I did mention about which still need GCC, and kernel is one of them, even though upstream has done a lot of work in making kernel work with Clang. In Yocto, we haven't done, or we are not using that yet. So for kernel, we still use GCC. glibc, there is some work, but it still primarily needs GCC to compile. And of course, the GCC runtime, which uses GCC as well, and some bootloaders. So I think there are like syslinux. U-boot is compilable with Clang, but it hasn't been tested, so it still is pinned to use GCC. So I think if some effort is put in there, probably many of those pinnings that you'll see in non-Clangable are probably removable. They are just that, you know, I or someone hasn't found a time to look at that in more detail. But these are key packages that you'd find are still needing, aren't using Clang actually. So there are some limitations. So for now, it is only used for target packages. So if you're having native packages, they still use GCC on your system. Chromium actually has taken a step further, and it's actually now using native Clang and native runtime even to build the native pieces of the build. But in general, when you use Clang, it doesn't replace GCC as a compiler for a native and native SDK packages. Relocatable SDK may not work. There are GitHub issues around it, and I think we understand the problem, but we haven't fixed it yet in a good fashion. So there are workarounds to use it, but I think we basically need to extend the patch to adjust for the LDSO path. And not all targeted packages will be using Clang. So be aware of that some packages are not compilable with Clang for many reasons. Some of them are because they're using some of the extensions that Clang has refused to port, and some are just not conducive to Clang because they don't use Clang to do regular development. So they introduce bugs that Clang finds and no one fixes them. So the others are undefined behavior in languages like variable length arrays in structures and things like that, which Clang won't accept. And obviously, if you have some architectures that are not the ones I mentioned earlier, and GCC has a longer list of supported architectures, Clang doesn't. In Yocto Open Embedded, if you're, I know there's a Arc support and C-Sky, probably you won't have Clang for them. Reproducible builds are untested. I'm sure there are bugs in there, at least in Clang itself, maybe to be reproducible, but that's something that remains to be done. So many of them are in wish list too. So this is, I picked up a little bit from the issues. So use Clang to compile the kernel and have some way in OE core to switch between or have multiple tool chains, and have a Yocto auto builder testing for Clang and some benchmarks, and MingW support, and LLVM runtime as default option tested as well. So there are more that are reported here. So if you are interested, chime in. And also include the additional tools perhaps in some form so people can use them easily in their projects. And LTO is a feature that's currently in OE core, has been added, hasn't been tested with Clang as much. So we would like to enable that by default in future. So that's all I had. Thanks for your time. And if there are any questions, or I think we are above our time anyway, but we can answer questions, or I could also answer them on the chat.